Good day, welcome to another YouTube video. Today we're going to be building a webcam-controlled rover, and now I'm going to let my partner to explain the fundamentals of how we're able to achieve this objective, which is to control the rover using the webcam.
Hi, I'll be presenting the code section for our project on webcam-controlled rover. Let's now dive into the technical heart of this project. The software architecture and the code implementation for this project. We primarily use MATLAB Simulink for the development of the code. The MATLAB live script handled our initial setup, as you can see from the slide. The crucial webcam images based imaging processing was done on the script. The core control logic for this project, however, resides in the Simulink model that gets deployed directly onto we use the Arduino Nano IoT board. The communication between the MATLAB and the MATLAB environment running on our computer and the Simulink model on the robot happens seamlessly over Wi-Fi with a TCP/IP protocol. Now we move on to our second part. At the lowest level of motion control is the differential drive kinematics. This is the mathematical model that translates the robot's desired overall movement, its forward speed, which in this case we denoted as v, its turning rate omega into like a specific speed requirement for the your left and right wheel. The equations are quite simple. The linear velocity of the left is the desired linear velocity minus the term relates to the turning rate, the wheelbase, and the wheelbase. And for the right wheel, it's plus the term because of its their own opposite sides. These calculated wheel speeds are converted into a PW signal, which controls the power sent to the motor, and adjusted by a minimum threshold to overcome your static friction. So for our next slide, we want to ensure that the accurate movement. So we implement a closed-loop PI controller within our Simulink model for both distance control and heading. The PI controller basically takes the difference between the desired position and angle, and the robot's actual position, and calculates the control command essentially. The proportional part of the PI controller provides an output based on the current error and gives a quick response. The integral part accumulates the error over time, which is essential for eliminating any small transient steady-state errors, ensuring that the robot reaches its target precisely. Looking at the program part for the rover, the Stateflow was used to manage your robot's high-level behavior. It's state machine where we define different operational states, such as your move forward, turning, and picking up and stopping. The chart transitions between these states based on defined conditions, basically. For example, the robot transitions out of the move forward state when the distance error falls below a specific threshold. The state-based approach is particularly effective at managing transitions and can inherently prevent overshoot by stopping the robot precisely when the conditions are met, rather than just letting a continuous controller potentially oscillate around the target. The state also calls the Simulink function that contains our PI controller algorithm to execute the necessary movement. Now for the localization to calculate the rover's position. Our robot sees the environment using the webcam and image processing, which is done in the MATLAB environment. The code localization happens within functions which are specified in the code. This function specifically takes the image from the camera, processes it, and then first applies a color threshold to create a binary image that isolates the red, blue, and green markers on the robot based on the color values. Then a filtering function happens, and then we clean up images, removing small spikes of noise within these images, so that we can see the shapes more clearly. So we use functions like I am close, I am open functions, which are a structured element. For instance, like your tray, and then we use another function, which the region function, to find the centroid, the exact center of the robot of our robot of each, so that each mark basically is cleaned. The robot's overall position is calculated as an average of these three centroids. Finally, the robot's orientation or heading is determined by calculating the angle of the vector from the robot's center point to one of the markers, like the red one indicating the front, using another function with adjustments to handle the different direction correctly. Now to get to the robot to navigate and move around the target, this is crucial localization data. To get the crucial localization data onto the robot, we use Wi-Fi communication. Our MATLAB script runs on the computer continuously, processing the webcam feed, and sends the calculated X, Y, and theta positions data wirelessly to the rover. Our Simulink model runs on the Arduino, and the Wi-Fi receive block listens for data on a specific IP port configured to receive three elements three elements double vectors representing the position. And for the final piece of the puzzle, our robot gets position information from two sources: the webcam via the Wi-Fi and its motor encoders, which provides odometry based on-the-wheel rotation. Both have strengths and weaknesses. Vision is good for global position, but not but can be noisy or lost. Encoders are good for relative movement, but can drift over time. Within our Stateflow chart, we combine these two data sources using weighted averages. We use a weighted average blending the vision data and the encoder data, assigning both the weight to the sensor we expect to be more reliable, which we expect to be more reliable at that movement to produce a more accurate and robust estimate of the robot's current position and orientation. If using, like, let's say, common filters for future work, a more advanced approach, which is a more advanced approach, like common filters could combine these inputs, considering their noise characteristics, to provide an even more optimal estimate. This fused position estimate is what the path and planning logic and the AI controller use to command the robot. So, in conclusion, in summary, the Stateflow chart decides the desired overall movement based on the fused localization, and the PI controllers. The PI controllers calculate the necessary linear and angular velocity and kinematics, and they convert these to the individual wheel speeds, and finally the speeds are translated into your PWM signals to send to the motor drivers to make the robot move. I'll give it to my classmate so that he can further elaborate.
To achieve the objective of this project, there are a few steps that we need to take. The first one is to characterize our motors, which simply means for each value between 1 and -1, we need to have one PWM value for each of those values, which is achieved by the second step is to calibrate the rover within our arena. Then after, the third step is to find the orientation and the location of the rover within the arena, and also determine the location of the target within the arena. These two codes need to be run every time there's any changes of the set type or lighting conditions. The final step is this lab script, where we are able to check the rover's progress as it follows the path that we've given it throughout this session in the arena. The final Simulink model looks like this, where we're gonna send it to the rover, which we're gonna use to control our rover. Now I'm gonna show you how each step was done and how the rover reacted. Now we're gonna do the calibration of each motor. This is our arena we've built, and this is the preview of our arena inside MATLAB. Now we are computing the offsets of the target.